Ok, boa tarde a todos. Bom, boa tarde a todos. Next speaker will be Douglas Arnold. It's actually quite hard to introduce Doug. I mean, one comment that I heard throughout my career is that he does everything, and that's true. I mean, so Douglas Arnold is McKnight, a presidential professor of math at the University of Minnesota. He defines himself as a researcher and an educator, and that's accurate. He was director of MIA for 8 years, roughly, and he was the president of CIM, the largest, applied and industrial mathematics community in the world. He has, of course, several papers, important landmarks papers, actually, and he's editor of several important journals. He is highly cited author, although he is quite critical of the use of prior use of citation numbers for gauging or measuring people. In particular, everybody should read the article Nefarious Numbers that he published in the notice of MIS journal. He has several international prizes. He was the speaker of ICM, a previous ICM, not the previous ICM, the one in China, I think, International Congress of Mathematics. He has a YouTube video on Möbius transformation that has millions of viewers. And when I say millions, it's not figurative number. It's not, that's the number. I mean, can you name a mathematical video with millions of viewers? Okay, he produced one. He actually did the math of golf. He has a talk on his page, and it's amazing. He helped to produce a commercial, a professional commercial that was broadcasted in the American TV, describing the math of golf, of playing golf. Okay, he was asked to measure the weight of a fish, a prize-winning fish. It was a contentious thing in Minnesota, I think, and okay, so through a photograph, an old photograph, he was able to estimate the weight of that fish. So what else? He has, and finally, okay, I'll be short, of course, it's a short introduction. He has some connections to Brazil. There is data showing or indicating that he had at least one Brazilian student, and maybe it's a time for a second one. And he was here 30 years ago in a mini symposium, in a workshop and call it Innovative Finite Element Methods, and he's back. And actually, you are all invited to come again on Friday for the session on that Marcus Sarkis and I are organizing on innovative finite element methods. Doug will speak again at 9 a.m. in the morning. So with further ado, Doug, please.
Thanks to Alex for that very nice and maybe over-the-top introduction. What some of you might not know is that Alex is one of my very best students, so you have to take all that with a grain of salt. It is interesting to see what aspects of your career your students decide that they want to honor on an occasion like this. It is a great honor for me to be here, and I've spent a little time thinking about how to give the talk to this audience. I see this is a grand tradition, the Colóquio Brasileiro de Matemática, and I was told over lunch that this is actually the first talk in numerical analysis in the 32 editions of it. So I did a quick check. In the last 5 years, 6.5% of the papers submitted to Math SciNet, the papers that have been reviewed in Math Reviews, Math SciNet, 6.5% are category 65, numerical analysis, compared to, for example, to choose the local favorite, 1.7% in dynamical systems, ergodic theory 37. So it's a good thing. It was a very wise choice by the organizers, maybe not to invite me, but to invite numerical analysis, and I hope it's the beginning of something. Nonetheless, I feel like probably most of the audience is not so familiar with numerical analysis, and I'm trying to reach out and make some connections. It's a very hot topic, this thing called structure-preserving discretization. In fact, this semester I'm spending time at the Isaac Newton Institute, where the main program is geometry, compatibility, and structure-preserving discretization. What is that? Well, hopefully you'll have a feeling for what that is as the talk goes on. The outline I have of the talk is, well, I'm going to start with a slide on the fundamental theorem in numerical analysis. I'll get back to that in a minute. But then I'm going to give an example of structure-preserving discretization for ODEs, where I think there's likely to be the most familiarity in this audience. That's symplectic discretization. And then I'll give an example for PDEs, which has been the main emphasis of my activity for maybe the last decade, called finite element exterior calculus. And I'll just try to give you an impression what that's about. And then I'm going to reverse things. Structure-preserving discretization uses ideas from other branches of math, like geometry, topology, a little bit of homological algebra and so forth, and applies it to getting the analysis and design and numerical methods for PDEs. But the last step is, the last topic is a reverse of that, where we actually use some ideas from finite elements to resolve what had been a long open conjecture in algebraic topology. Why am I starting with the fundamental theorem in numerical analysis? If this was an analysis course, I wouldn't start with the fundamental theorem of calculus, because I'd assume you all know it. If it was an algebra talk, we wouldn't do the fundamental theorem of algebra. But I bet, I won't ask for a show of hands, but I'll bet almost nobody in the audience knows what the fundamental theorem of numerical analysis is. So let me give you an idea. It's good because it's going to give us the vocabulary we need for the rest of the talk. So what do you try to do in numerical analysis? Well, you try to solve an equation, basically, where the equation could be a very complex thing, like a partial differential equation involving boundary conditions and initial conditions and so forth. But let's abstract all that and call it LU equals F. So you have a space of possible data F, you have a space of possible solutions X, and you have an operator that maps L that maps the space X to the space Y of solutions to data. I'll assume for the purpose of stating everything in the simplest possible case, let's take it a linear operator. So we're given little f in y, and we want to find little u in the solution space X such that LU equals F. Okay, and what we do in numerical analysis, computational math, is we take that, which is probably a big, complicated, infinite dimensional problem, and we reduce it to a finite dimensional problem, that process called discretization. And so discretization means you construct new spaces x little h and y little h, and they're finite dimensional, and you construct an operator L little h from xh to yh, which should be invertible, and then you construct a piece of data fh and y little h, discrete data, and you solve LHUH equals FH. Okay, that's discretization. You can't prove a theorem at this point, because there are no hypotheses, right? The only relationship between L little h and L is that they both use the same letter. But they have to be close to each other in some sense. The h is an indicator of discretization, and usually it's a mesh size or a grid spacing or something that indicates how far you've gone in the discretization. And our goal is that when h is taken to be very small, UH is in some sense close to U. So there are three definitions that go into this, and out pops the theorem. So the first definition is, how do you measure what you mean little UH is close to little u? You can't really compare them because they live in different spaces. One lives in X, one lives in XH. So what you do is you take what's called a representative, capital U, of little u in XH. That's something in XH that we all agree is close and we'd be happy to get. The typical example would be if u is a smooth function, and then you take a grid for you take functions defined on a discrete grid for your XH, the representative would just be the restriction of the function to the grid. Okay, And we need to assume that we have a norm on the space xh, and then we can measure the difference between the representative of the true solution and the discrete solution. And the goal is to make that small, and we say the method converges if that goes to 0 as h goes to 0. The second definition is called consistency error, which is a totally different kind of error. And these things sometimes get confused, but they're very different. The consistency error measures how nearly the true solution satisfies the discrete equation. So roughly speaking, you take LHUH equals FH, and you stick in the real U, not the UH. But actually, that doesn't make sense because it's not in the right space, so you stick in the representative capital U, LH of capital U minus FH, and you measure that using the norm for the discrete space YH. And the method is consistent if that's small. That's the thing that says LH is really close to L in some sense, and the data FH is really close to F. And that method is called consistent if that thing goes to 0. Okay, and the fundamental non-theorem of numerical analysis is that if a method is consistent, then it's convergent. That's not true. We're missing something key, and that's the third definition. The stability constant, by the way, you would be surprised at how many practitioners, people who use numerical methods in their daily life and work, don't appreciate the role of stability and think once they've checked consistency, they're safe to use their method. And occasionally an oil platform crashes to the ocean floor because of something like that. Stability is measured by a constant which is measuring the well-posedness of the discrete problem. Remember, Hadamard said that the problem LU equals F is well-posed if it has a unique solution, and small changes in F lead to small changes in the solution U. We apply that to the discrete problem. Small changes in FH should lead to small changes in UH. A linear problem that can just be measured by the norm of the inverse, that's called the stability constant. And we don't want that to be very big. We want it to stay well posed as h goes to 0, and that's the definition of stability. Once you have those three definitions, the theorem is very easy to prove. There's a basic estimate which says that the error is bounded by the stability constant times the consistency error. If you know any functional analysis, you can prove that just from the definitions. And therefore, if we let h go to 0, a discretization which is consistent and stable is convergent. So I'm going to show you a bunch of examples of discretizations today. And since I'm trying to compress a lot of stuff into one talk, first I'll show you things that are like most numerical analysis. They work well and everything is great because they're stable and consistent. And then I'll show you some that don't work well, that they go wrong on you. And you should ask, why did it go wrong? It has to be according to this theorem. Either it's not stable or it's not consistent or both. Okay, now let's get to the main talk. By the way, is there, oh yes. So discretization of ODEs. So an ODE, let's take a simple ODE. It could be scalar, it could be vector ODE. U dot is GU. Let's say it's happening in R or Rn with some initial condition U of 0 equals U0. That's our problem LU equals F. So L is taking the function U and returning the function U dot minus G of U, which it would like to make 0. And it's also returning the initial data U0, which it would like to make little U0. So this fits in our framework, as most any well-posed problem will fit into our framework. So now we want to discretize it. So let's go back to the simplest of all methods. It goes back to the master of us all, Euler. So the idea is to replace the space of all functions, all C1 functions, with the space of just grid functions. So that means you take the interval you're doing the numerical integration on, you divide it into a grid of points, 0h, 2h, 3h, with a spacing h, which is presumably very small. And you have a function defined only on the grid points. That's a grid function with values u0, u1. So of course, it's just Rn in disguise as a grid function. And if you have such a grid function, you can define an LHUH on it by using the definition of the derivative is the limit of difference quotients, and we use one of those difference quotients, the spacing h. So this is our approximate L, and we don't even have to approximate the initial data. We can just use the initial data. That's our discrete problem. And now I'm going to run a little video, and I'm not sure it's going to work. I may have to pop out of the talk, but let me give it a try. So what I did here in the left one, I took a pendulum, put it almost perfectly vertically, a tiny little bit off center so it didn't stay vertical for all times. And I let it go for 20 seconds. I solved the nonlinear damped pendulum equation. U double prime is equal to minus sine u plus a damping term written as a first order system. And I just applied Euler's method, and then I did a visualization of it so it looks like a pendulum. And let's see if I can get it to go here. Okay, it's very choppy, but that's actually not what it looks like. I'm going to slow it down in a second. You'll see what it looks like. It actually, it's not worth my stopping and pulling out the video player, but it actually looks like a very nice pendulum. It swings back and forth and slowly dies away. So I don't know if there's any chance it'll do better if I do it again. No. Okay, now let me do it again in slow motion. This one I think is smoother. And I made one other change. Not only did I do it in slow motion, but I'm doing two pendulums. There you can begin to see the other one. So that's what it looks like. It looks like a reasonable damped pendulum, the green one. You might say, well, that looks good, must be about right. You used a lot of steps, 20,000 must be about right. But the blue is about right. The green is not about right. The blue was done again, but with a much more accurate numerical method, Runge-Kutta fourth order method. So this shows, first of all, don't believe videos by computational mathematicians. The picture can look good, but that's not a norm. The eyeball norm is not a norm. And you see that these things are totally different from each other. There's very little accuracy in the Euler's solution. So how do you get a better solution? Well, there's Euler's method up there. And how would we measure the error in Euler's method? Well, we would look at the consistency error and ask whether it's stable. The consistency error of Euler's method, how do you do that? Well, you have to put the exact solution at the grid points into the u here. And you remember the g of the exact solution is just u prime. So it's the difference between the difference quotient and u prime. Use Taylor's theorem, and you get that that's order h. So the error is proportional to the size of the number of steps. And that wasn't enough to make it very small. There was a 49-degree maximum error in that little video. Here's another method which is a little better. You use a difference quotient where one point is pushed ahead and one point is pushed behind, and the place where you evaluate g is in the middle. That one you can easily check has a consistency error of order h squared. Both of these methods are stable, and the result is that this has a much smaller error because h squared is much smaller than h. That error, you probably wouldn't notice it on the screen. Then I went a little further. If you're going to use un plus 1, un, and un minus 1, you may as well consider evaluating g at un and un minus 1. And there is a method that uses those two evaluations of g and this combination, and it's third order. It's the only third order two-step method. That gives you order h cubed. I'll say something more about that method in a minute. And then there's the one that I use for the blue, so-called correct answer. This is the Runge-Kutta method. That uses 4 different evaluations of g. Some of them are hidden in this dots. They're all easy to program up. They're all stable. Well, sorry, that's not true. This one is stable, and its consistency error is order h to the fourth, and that one has an error of 0.000048 degrees. That's why I say it's basically the exact solution. What about this third order method? I didn't tell you how much error that causes. I'll show you the video on that one. And that one, the video jumps around again, but it's supposed to. That's actually what it looks like. It doesn't look anything like a pendulum. And the error it causes is 10 to the 14,000 in 20 seconds. So what's wrong? Everybody knows. What's the matter with this problem? It's more consistent than the two above it. So it must be unstable. It's totally unstable. Small changes in the data lead to large changes in the solution. How come? Can we see that? Well, I'm going to demonstrate this on the simplest possible ODE. We will all agree this is the simplest possible ODE. U prime equals 0, whose solution are the constants. If we take this method and apply it to u prime equals 0, we get un plus 1 is minus 4 un plus 5 un minus 1. You can write down the exact solutions of that. They're any constant epsilon times minus 5 to the n. So epsilon minus 5 epsilon, 25 epsilon, minus 125 epsilon. Those are the grid point values. So let's say I take my initial data, not to be 0, but I take it to be 10 to the minus 10. Then you multiply that by minus 5 to the n, and you find after 20 time steps, your solution is at 95,000. It's supposed to be between pi and minus pi, but it's at 95,000. That's instability. This tiny little epsilon data led to an immense solution. Such methods don't work. Not because of the PDE, the ODE, which is just the pendulum equation, or even u dot is 0, but because of the numerical method. It's not consistent. Okay, that's fun and games. Let me get to a real problem now. This is from a famous 2009 paper by Jacques Lascar and Gaël Gastineau. They simulated the evolution of the solar system using Kepler's equations, using Newton's equations, for 5 billion years to answer whether the solar system was going to be stable for that time, help you plan your real estate investments. They didn't only do it once, they did it 2,500 times. And that's because they don't know the initial data exactly. We know the initial data very well, but not exactly. And it turns out small errors in the initial data lead to large errors in the solution. This solution is pretty well posed, but not that well posed. It has large Lyapunov exponents. So they varied the position of Mercury by 0.5 millimeter for each of the 2,500 times. And here they plotted all 2,500 solutions they got. And you see, most of them, they're plotting the maximum eccentricity of Mercury, because when Mercury becomes very eccentric, the solar system destabilizes. And you can see there are a number of cases where that happens. It's pretty much impossible, except for very special cases, out to 3 million years. But then it gets about 1% of the orbits are unstable in this sense. So the question that I want to ask, how the hell did they compute 5 billion years accurately? And they did. This is an example of, this is initial data of Mercury, Venus, Earth, and Mars. They're not showing, the other planets are way out here. They did all of the planets. And this is what happens in one of the simulations after 3 billion years. And you see Mercury has become very eccentric, and we've reached the point where at one year or another, as Mercury and Venus orbit each other, they're going to come into close encounter or collision, and we'll have disaster. Let's see, this I think doesn't work. So at this point, I'm forced to want to show you this video. Okay, this is a video made by Lascar and Gastineau. Oh, I have a great view of it. What's wrong with you? Let's see. Okay, let's get that started. So that's now. And as time goes on into the millions of years, and then getting near 1 billion years now, I think, you see some precession and distortion of the orbits, but nothing that's to cause concern for the first hundreds of million years. But when you get to giga-years, some of the, depending on the initial data, some of the solutions become very eccentric. And you have the possibility of collision between almost any of the 4 inner planets. And of course, you don't have to have collision if there's a very near passage, then a planet will be thrown way out into space or something. Otherwise, disastrous will happen. And Lascar and Gastineau even should give us a psychological idea of what might happen. That's coming up. Even collisions between Venus and Earth, or Mars and Earth. So it's time to sell. How do I get this out of here? The last part was not done by simulation. You shouldn't believe it. Okay, let's see. Sorry, give me a moment here. Oh, it's taking a while. So the question we want to ask ourselves, I'm not up to the pendulum yet. Question we want to ask ourselves is how did they do such an accurate computation? And, okay. So I'm going to investigate that question by looking at a simpler problem. Instead of looking at a simulation of all 9 planets for 5 billion years, I'm going to look at just one planet going around the sun, so just Kepler problem, for 500 steps per period and for a couple of hundred periods or something at maximum. Let's see if this one will run. So this is using the Runge-Kutta-4 method, the one that was good, that gave the blue curve that was an accurate one. And we're computing, well, Kepler's laws say this should be a closed orbit, a closed ellipse. We get something that looks sort of like an ellipse, but not quite because it's not closed. So this method doesn't give us very accurate answers, and if we wait a little while, we'll get a close approach to the sun, and this is what happens after 170 periods. So this method doesn't work. This was the good method, the Runge-Kutta-4 method that gave us an error of 0.0000 something before, but it's not good enough for even solving the Kepler problem for one planet for a couple of orbits. So let me show you a slightly different method. This method was invented by Mary Paz Calvo in her thesis in the 90s. She's at Valladolid. And it's very much like the Runge-Kutta-4 method, only you change some of those coefficients, those halves and quarters change to some other numbers that she cleverly calculated out to 18 decimal places. And this is what no, that's not what you get. This is what you get if you look at her method. And it'll keep doing that. The orbits are closed on this. Even the discrete orbits are closed. They're not almost closed. They're not closed to 0.000. They're closed. That's crucial. That's what structure-preserving discretization is about. So how do you do that? Well, let's go to even a simpler problem. Instead of comparing Calvo's fourth order method and Runge-Kutta fourth order method, let's look at just the Euler method, which does not have closed orbits, and something called the symplectic Euler method, which does. So this is the same problem, just calculating an elliptical orbit. And here I've written the second order Kepler equations. The derivative of position is equal to velocity. The derivative of velocity is proportional to 1 over the distance from the sun squared. So I've written that Euler's method the way we did it, the way we had it before. This is it applied to a system. And you see that we don't get closed orbits. In this case, it doesn't wander in, it wanders out. But we have a big problem. It's not going to give us accurate solutions. Here's another method that's called the symplectic Euler method or the Sturmer-Verlet method. It's an amazingly beautiful method with a lot of structure behind it. And look at it, it's completely simple. The first equation is exactly the same as Euler's method. And the second equation is the same as Euler's method, instead of using xn, use xn plus 1. It's just as easy. So you really, literally in your code, you add plus 1, and you run the same code again. And then you get nice, beautiful closed orbits like this. So what's going on? That's what's known as symplectic discretization. So I'm talking to many people in the audience who know much more about this than I do, but let me just briefly review Hamiltonian systems. All the equations I've looked at so far, if you ignore the damping on the pendulum, are Hamiltonian systems. They have the form that there's a vector variable, the momentum or the velocity p dot, which is minus dh dq, and there's a position variable q dot, which is dh dp, where h is a function of both variables p, q in the real numbers, the Hamiltonian. Having this form is equivalent to saying that the flow map, which takes you from the initial data p0, q0 to the data at some time t, pt, qt, that's the flow along the dynamical system, that's a symplectic transformation in the sense that it leaves invariant this symplectic 2 form, this dp1, dq1 plus up to dpd, dqd. If you haven't studied this stuff, then you probably don't know what it means to leave invariant a 2 form, but don't worry about it too much. There's a certain invariance on the phase plane PQ of the differential of the flow map. That's a Hamiltonian system. And so a classical example is the pendulum equation. Probably many of you have seen the phase plot of the pendulum equation here. And there are the pendulum equation. Q dot is P and P dot is minus sine Q. That's a Hamiltonian system with this Hamiltonian here. And since there's only one P and one Q, to be symplectic means to be volume preserving. And what that means is that if you take some initial data, like you take this little red rectangle of initial data, each of these points is one value of P and Q, so one initial data. We have P on the x-axis, Q on the y. Here's another bunch of initial data, and here's another box of initial data. And then you let it flow forward in time according to the ODE, and you get that. And they get distorted. They're not quite rectangles anymore. If you do a bunch of them, they're definitely not rectangles anymore. But they preserve volume. The area of the boxes is the same. That's what a symplectic flow is, and that's what a Hamiltonian system does. Okay, now let's discretize it. So let's switch to Euler's method, or symplectic Euler method, or Marie-Pascal's method, or something like that. Then the flow becomes discrete. It doesn't take to any time t, it only takes to discrete values, pn, qn to pn plus 1, qn plus 1 to pn plus 2, qn plus 2. But it's a flow on the whole phase space. The pn, qn can be any point on this phase space. That's not discretized. And so we can ask, is that flow symplectic? Does that preserve area? And the discretization method is called symplectic if that flow is symplectic. And that's the difference between Euler's method and the symplectic Euler method. You see, in Euler's method, after a little flow forward, the volume of the data changes quite a lot. It gets bigger. Well, here, in the flow of the symplectic Euler method, it stays the same. How do you see that? Well, you use this. Okay, this. So what's backward error analysis? Ordinary error analysis says, how big's the error? That is, how much did I change the true solution when I switched to the discrete solution? What error did I introduce? Backward error analysis said, how did I change the problem? The discrete solution doesn't solve the problem anymore. What does it solve, and how far is that from the right problem? So here's an example, this pendulum example again. So the blue is the orbit of a real pendulum satisfying the pendulum equations that are over there. The red dots are Euler's method. So you could just look at that and say, well, the red dots drift away from the blue, there's an error. But you could look more deeply and say, well, the red dots are obviously on some sort of spiral themselves. They're sort of solving something. What do they solve? And it's easy to figure it out. They solve this ODE. Q dot is equal to P plus H over 2 sine Q. And P dot is minus sine Q plus H over 2 P cos Q. If you solve that exactly, you get the red dots, the Euler's method. So Euler's method is solving the wrong problem exactly. That's what backward error analysis tells you. Do the same thing for symplectic Euler, and the only difference you get is that the sign of this plus h over 2p over q becomes a minus sign. So what? Same size, minus h plus h, so what? Well, so what is that this one is a Hamiltonian system, this one is not a Hamiltonian system. That's why this is a symplectic method, and that one's not a symplectic method. Okay, so now let's go back to Lescar and Gastineau. How did they simulate the solar system for 5 years? Well, they didn't use any of the methods I've told you. They used a method called SABA-4. It was derived by McLaughlin in '95 and modified a little bit by Lescar and Rubel. The derivation of this method is very complicated. It involves very deep mathematics, Lie theory, the Baker-Campbell-Hausdorff formula for commuting exponentials and things like that. The key property of it, or one key property of it, it's symplectic. So they use the symplectic method. By the way, why does it matter why it's a symplectic method? I should have probably mentioned this here. Symplectic methods are Hamiltonian, and Hamiltonian systems, as those of you who study dynamical systems know, have all sorts of nice properties, like there's no damping, there are many closed orbits, there's no sources and sinks, and so forth. And so symplectic methods are going to have Hamiltonian dynamics, closed orbits and things like that. So that was why it's very important that it's symplectic. It has another structure-preserving property called time symmetry, which I won't get into. They did 200 billion steps to cover 5 billion years, so that's a time step of 9 days. And what order was this method? Was it first order like Euler? Obviously not. Was it fourth order like Runge-Kutta, eighth order, 100th order? Well, it was second order. That might come as a surprise. You say, why would a second order be accurate enough? But it's not really accurate. You have to look at the consistency error a little more deeply than just ask what power of h it is. They exploit the fact that when you compute the solar system with 9 planets, it would be easy to compute the orbit of each individual planet without the effect of the others. It's the interactions that make the n-body problem complicated. But you get pretty close by just letting each planet stay on its own orbit. That'll give you a rough idea. And that'll be off by a factor that'll depend on the relative mass of the planets to the mass of the sun, and the planetary mass to the solar mass, which is about 1/10 of 1%. So SABA 4 is very cleverly designed so that the consistency error has a factor not only of h squared on it, but also of epsilon squared. So this gives us an extra 6 decimal places. This is huge. And then the next term in the error is order h to the 8th, and it even has an epsilon. So this is a very small consistency error, which explains how they could get such high accuracy. Okay, so that's structure-preserving discretization in the form of ODEs. So now I'm going to do PDEs, and first I have to teach you finite elements, and then when we do that, we can talk about structure-preserving finite elements. So here's finite elements on one slide. You want to solve the mineral surface equation, which I'll first put in a variational form. What we want to do is we want to find a function defined on this square here, function of 2 variables. It should pass through these 2 curves. Think of a soap bubble attached at the ends to those curves. And we should have minimal surface area, which means that this integral over the square should be as small as possible. Find the function u that makes that happen. You can take the Euler-Lagrange equations of that, essentially differentiate it, and you get a weak equation which looks like this one down here, or if you integrate by parts, looks like this. So I'll first write this. This is called the minimal surface equation. It's a second-order nonlinear PDE. And I'm going to use this weak form for finite elements. So finite elements use the weak form. We're trying to find a function u, which interpolates the blue curves, such that the integral of grad u dot the gradient of any other function v over this square root is 0 for any v. That stationarity is the same as saying that this has a minimum. And where is u and v? Well, sorry, u and v are in spaces of functions where this makes sense, like a Sobolev space. But now I'm going to do discretization. I'm going to discretize this weak form by not looking for any function u, but only functions used in some finite dimensional space, vh. So this is the discretization. You put h on everything. Look for a function uh in a finite dimensional space vh to be specified, which interpolates the curves and satisfies the equation we wanted for all v in the same finite dimensional space. That's called Galerkin's method. Many numerical methods are a form of Galerkin's method. And the finite element method is when you take your domain, you triangulate it, and then you take a space of piecewise polynomials with respect to that triangulation of some given degree, or something like that, as your space VH. Like here's the space of piecewise linear, continuous piecewise linear functions on that triangulation. There's one example. So you try to solve this, and that turns out to be a system of n equations and n unknowns, where n is the number of vertices of this mesh. And computers can do that very well, even when it gets up to millions of equations. And if you do it, you get that. Not on the mesh I showed, on a somewhat finer mesh. And you get this beautiful surface, which gives you the minimal surface on this. OK, so that's how finite elements work. You take your problem, you cast it into weak form, you restrict your test and trial space to finite dimensional space made of piecewise polynomials on some triangulation. So let me give you another example. Let's say we want to find the eigenvalues and eigenvectors of the Laplacian on this slightly asymmetric square annulus. So we want to solve minus Laplacian u is lambda u. U is 0 on the boundary, but u is not constantly 0. We've cast it into weak form, which means we look for this is the space of all functions for which the gradient is square integrable and which vanishes on the boundary, H01. And we look for all functions in there such that the inner product of the gradient of u with the gradient of v is lambda uv. That's what happens if you take this equation, multiply it by the test function v, and integrate it. Integrate the Laplacian by parts. And now we do Galerkin's method. So we cut our domain into a bunch of little triangles. And we take functions. Again, I showed you a picture of a piecewise linear function on that triangulation. And we look for h in that space and restrict the test function v to that space. That's an eigenvalue problem for a matrix. There are ways to solve that on the computer. And this is what you get. It tells you that the first eigenvalue is about 9.279, the second's about 11.245, and the corresponding eigenfunctions look like this. That's if I use about 4,000 triangles and piecewise linear finite elements. P1 means piecewise linear. To get some feeling how accurate that is, I'll do it again with more triangles and higher degree polynomials, 16,000 triangles and piecewise polynomials of degree 4. And then you get 9.19, meaning the first one was off by about 1%. Not too much. And if I go even further, these numbers don't change, and we see that we've got the answer probably to all 5 decimal places. OK, so again, the finite element works well, and it's used every day for thousands of things in Brazil and everywhere else. OK, but here's a different story. So now I'm going to show you something that goes wrong. This is much less common. But this is what we want to study. So it depends whether you're a geometer or an analyst. If you like exterior calculus, you would write the Hodge-Laplacian as d star d plus dd star on one forms. If you're studied vector calculus, you would think of u instead of one form as a vector field, and you'd want its curl curl minus gradient div. And we want the eigenvalue of that with some reasonable physical boundary conditions. We cast that into weak form. The inner product of du with dv plus the inner product of d star u with d star v is lambda uv for all v in one forms or in vector fields. And we do the same thing we did before. Cut the domain into triangles, take piecewise linear vector fields, and compute the first 3 eigenvalues and eigenvectors. And it's 1.94, 2.02, and 2.26. Unfortunately, I used a better method than this, and I computed the answer to high accuracy. This is the correct answer. Actually, before I do that, there's a little quiz for the geometers in the audience. How do you know that this is not right? If you've studied Riemannian geometry, you know that the Hodge-Laplacian on one forms has a kernel whose dimension is the first Betti number. That's de Rham cohomology tells us. That means the hole in this domain says there's a kernel to this operator, so its smallest eigenvalue is now 1.9, it's 0. Must be. And here's the truth. So the first thing is what a perfectly reasonable method calculated, and the second is the truth. There is no relation between them. This is fake news. So why did we get fake news out of the standard finite element method? Will it go away when we refine the mesh? Well, here I did a little convergence study. I used these regular piecewise linear finite elements, and I computed the first 6 eigenvalues with 64 elements, 256 elements, 1,000 elements, up to 1,000,000 elements. Everything converges very nicely. And unfortunately, what it converges to is not the truth. It converges very nicely to something that's completely false. Here are the true eigenvalues, and these curves don't converge to them. I use methods based on the finite element exterior calculus, which is what I'll be talking about. And here are the curves, and they converge very nicely to the true eigenvalues. The bottom one is 0, like it has to be. And the next one is about 0.6, and so forth. So the standard method, the takeaway from this is the standard method is a disaster in this one, even though it seemed like the same thing that worked just fine for the scalar Laplacian. So the answer is why, and what do we have to do about it? Well, I'm not going to say much about why because I don't have time, but I'll give you a little hint for the more expert in the audience. This little red dot here is an important giveaway. There's a big singularity at those reentrant corners, those non-convex corners. And the P1 finite elements are not able to match those. They cannot capture that singularity. That leads to a large consistency error. So the problem is the standard method is inconsistent. And this other method I have, which I didn't explain what it was, is consistent. Here's another example that I love that I first learned from Brezzi, Bofi, and Gastaldi, which is something called the Maxwell eigenvalue problem, closely related to what we just saw. In calculus terms, it would be curl U, curl V equals lambda UV. And if you solve it on a square, no holes in the square, then the exact eigenvalues can be computed by hand by separation of variables, and they're just the sum of two positive squares. So they're 1 plus 1 is the smallest one. So the first eigenvalue is 2. The next one is 2 squared plus 1, or 1 squared plus 2 squared, so 2 eigenvalues of 5. Okay, I solved this exactly on this mesh. There are no reentrant corners on this mesh. There's no consistency error problem. And a strange thing happens. We see the first things, as we refine the mesh, converges nicely to 2. The next numerical eigenvalue converges nicely to 5 and 5. And then the next one converges to 6. Well, check out writing 6 as a sum of 2 squares, and you'll have trouble. Now we get the number theorists in the audience involved. Those two are completely spurious. So this is fake news again, but a more dangerous fake news because it looks like it's working. That happens only on certain meshes like this crisscross mesh. That's another failure of P1 finite elements, and this one is due to stability, not consistency in a complicated way. If you do the same method using the finite element exterior calculus approach, there's no problems. None of these are spurious. They're all accurate. What are these two different methods? Well, let me try to help you read this picture. This is the way we picture a finite element. This is talking about piecewise linear vector fields. Because if you take a big triangulation, you go to one triangle, you go to each vertex, you specify two numbers, the two components of your vector field. Then you can interpolate that by linear vector field on the triangle. It'll be uniquely determined because 3 points determine a linear function in 2 dimensions. And as you put those together from triangle to triangle, you'll get all continuous piecewise linears. They'll all be of this form, piecewise linear in each component on each triangle. So they're determined by these functions, linear functions on each triangle, and by their degrees of freedom, the value of the two components at the vertices. That's a good way to compute many things, but it's not a good way to compute one forms, it turns out. These are the finite element exterior calculus edge elements, which actually go back to Raviar and Thoma in the 70s in this simple case. And these ones, the shape functions, are something a little more complicated. You don't have all linears. The first component is only things that are linear in the y direction, but constant in the x direction. And the second one reverses them and keeps the same coefficient b. So that particular three-dimensional space of functions is your shape functions. And your degrees of freedom are on the edges, not on the vertices. They're the integral of the tangential component on the edges. That's suited for one forms. Feels maybe like if you know what differential forms are, a one form can be integrated on a one-dimensional manifold. So it can be integrated on the edge of a triangle. That's what these are based on that. Okay. So finite element exterior calculus is a theory that's now getting sort of old, decade and a half or something, which is an approach to trying to design finite elements that work for a variety of PDE. Based on capturing essential structures. Like for the ODEs, we tried to capture the symplectic structure. Here we try to capture things like differential complexes, which have a cohomology. We try to capture their cohomology, their Hodge theory. And and related quantities to that. And what's more, we try not only to capture them at the discrete level, but we try to relate the discrete quantities to the quantities at the continuous level. We've captured all this in something that's a mixture of geometry and functional analysis called a Hilbert complex. Before I get to that, let me just give you a tiny history. I was honored to give a plenary lecture at ICM in Beijing. That was the year that Jacobo Pallas was the president of ICM. And I had the first ideas of this theory at that point. So the paper published for that is sort of the introduction of this theory to the world. And then I worked very hard with my colleagues Rick Falk from Rutgers and Ragnar Winter from Oslo. And we produced these 2 long papers, which is where the basis of the theory came. The Hilbert complexes were introduced in the second one. And I had just published a book last December in SciAm, which is pretty cheap, and it's also downloadable from the SciAm site if you have a license, which now is probably the reference place for the theory, or a way to get introduced. So what's a Hilbert complex? Well, it's modeled on the de Rham complex. What's the de Rham complex? Well, you take differential 0 forms, which are just functions, and then you take differential 1 forms, which are roughly speaking vector fields, covector fields, and you take the exterior derivative between them, which is a sort of gradient operator. And then you take the next exterior derivative to 2 forms, and the next and so forth to n forms. That's called the de Rham complex. It's a complex means that D composed with D is 0. But notice these are not bounded operators. I'm doing this on L2, and the gradient of an L2 function typically won't be an L2. So we're talking about closed, densely defined operators. And then they have a domain, which is exactly the functions for which this D makes sense, takes L2 to L2. And I guess I'm going to have to skip over a lot of details here. But when you have such a complex, you can compute its cohomology, which is the null space of 1D divided by the range of the previous D, quotiented by the range. That has the dimension, the Betti number, so that has a lot of geometry in it. And then because we're in an L2 setting, a Hilbert space setting, we can realize this quotient space as an orthogonal complement, which means we can realize the cohomology space as a subspace of the differential forms. We can realize them as differential forms, the harmonic forms. And the other thing we can do when we have a inner product is we can take the adjoint of these operators D and get operators D star going backwards. And therefore, we can form an operator that says take D to the right and D star back to the left, and add that to D star to the left and D back to the right, and you get the Hodge-Laplacian that we saw before, which is well posed up to harmonic forms. The harmonic forms measure exactly to what extent that is or is not well posed. So we abstract that to a Hilbert complex, which is basically a complex of Hilbert spaces and closed densely defined operators that have those properties that I just mentioned. And out of that, we get a Hodge-Laplacian at every level k. So we get a lot of sort of PDEs, but on an abstract level. In a similar way, we get heat equations, wave equations, eigenvalue problems, and so forth. And there's lots and lots of examples of this. For example, if you want to do Darcy flow equations, which are very popular here, or Maxwell's equations, which are very popular everywhere, or elasticity equations, they all fit in as Hodge-Laplacians of some complex like this. And now the basic idea is of finite element exterior calculus is if you want to discretize the Hodge-Laplacian associated with some Hilbert complex, your discrete method should have a discrete Hilbert complex that should have those same kind of properties. And so this is one of the major results of finite element exterior calculus. What are the properties that you need to have? For each of the differential form levels, lambda k, you need a subspace of the domain space h lambda k. So we have a space of 0 forms, finite dimensional, discrete space of 0 forms, 1 forms, 2 forms, and so forth. They should form a complex themselves. D of one of them should map into the other. That's the subcomplex assumption. That's the first structure preserving property we need. And the other is a little more complicated, that if I put the original Hilbert complex on the top, like I did here for the de Rham complex, and I put the discrete Hilbert complex on the bottom, I'm just showing you a little piece of it I did for this here, there should be projection operators mapping down from the top to the bottom, and they should be cochain projections. They should commute with D. If you have those two properties, then all the nice structure from the continuous problem carries down to the discrete problem. That's the main message of finite element exterior calculus in the abstract. In particular, the cohomology of the discrete problem captures the full cohomology of the true problem. That's very important. If there's harmonic forms for the true problem, that means your original problem wasn't well posed. You have to give some side conditions to get a unique solution. Well, you better be able to give those same side conditions on the discrete problem, or else you'll never capture your problem on the discrete level. This says that that's the right number of side conditions for the discrete problem. That's an example. Okay, then comes the other big part of finite element exterior calculus. We probably don't have time to go through it. But so the first part is this theory of Hilbert complexes and how you discretize them. And we have certain conditions that lead to good discretizations. The second part is you take a specific real complex, like the de Rham complex or other complexes. How do you actually get spaces that satisfy that? Of course, I want to use finite element technology. I want to get spaces of piecewise polynomials that get to that. And I'm not going to go through this slide except to mention a couple of things. For the de Rham complex, it's completely worked out. It's based heavily on the Kazul complex, so it turned out that was just the right tool for this. It led to two families of differential forms that are indexed by a polynomial degree R, a differential form degree K, and a triangulation TH. It works in any number of dimensions. There's something similar also for cubes instead of simplices. And it actually makes a beautiful periodic table of finite elements. So here, the first three rows are the first three polynomial degrees in one dimension. The second three are the 2 dimensions and 3 dimensions. If I could draw it, this could go on to 4 and 5 dimensions. This is one of the families on simplices. This is the other. And those were these elements that worked as opposed to the elements that didn't work. It's all completely systematic and completely automatically generated from the theory. Leaves open, that's for the de Rham complex. It leaves open the question of other complexes, and that's what I'm going to be talking about on Friday morning. Oh yeah, this thing is online. And in fact, if you really like it, I'll mail you one. Send me an email. Okay, and I'm going to end up, I think I have 10 minutes? So I want to end up going the other way. So where we are now, we've saw 2 examples where ideas from dynamical systems in the first one and from symplectic geometry and ideas from algebraic topology and Hodge theory and functional analysis helped numerical analysis design and analyze good numerical methods. Now I want to turn around and tell you about this fun story we had. This is joint work with Johnny Guzman, who's here in the audience, and also Gantmer, Sok Terrell, and Richard Falk, where we realized that there was a problem in the topology literature that could be understood as a finite element problem, and we were able to solve it. So it ties back to the periodic table of finite elements. One of those 2 main families was the PR minus family. R is the polynomial degree. PR means polynomials of degree R, minus means not quite, something less than full degree R, and K is the K forms. And those are defined on a simplex of dimension n, giving you pictures like this. Well, this picture we saw before in 2 dimensions. Here it is in 3 dimensions. That's shorthand for continuous piecewise linear functions on a simplicial triangulation. On each vertex of the tetrahedron, you give a value, and that determines a piecewise linear. And there is a terrible typo on this slide, which I didn't notice before. Completely wrong. This is P1 minus lambda 0, not P0 minus lambda 0. This is P1 minus lambda 1, P1 minus lambda 2, and P1 minus lambda 3. I don't know how I did that. But these are actually in the table. Where are they? These are the first ones in the first green column. There's for the P1 minus lambda 0, P1 minus lambda 1, P1 minus lambda 2, P1 minus lambda 3. These are these sort of fancier finite elements I showed you one example of before, where you have sort of complex shape functions, which are actually explained by the Kazul differential. And these are known as Whitney forms because they were actually first invented. That is, the piecewise polynomial differential forms of this sort were invented by Hassler Whitney in his 1957 book, which is several years before the term finite element was invented, or the finite element method was invented. So he had no idea of finite elements, was not interested in numerically solving PDEs, but there's a lot of geometry here. The zero forms are determined by giving one number on every vertex. The one forms are determined by giving one number on every edge. The two forms are determined by giving one number on every face, and the three forms by giving one number on every tetrahedron. So there's a lot of geometry there. In fact, these are in one-to-one correspondence with cochains, zero chains, cochains, one cochains. A one cochain is something that assigns a number to every one-dimensional edge of a triangulation. Okay, well, Dodzuk and Patodi in the 70s were trying to prove the Ray-Singer conjecture, which is from algebraic topology. And for this, they had to get some control over eigenvalues of the one-form Laplacian, and in general, the k-form Laplacian, the Hodge Laplacian. And they did this by defining what they called the combinatorial Laplacian. So they want d star plus d star d. Well, d is defined as the differential operator, the differential in the cochain complex. Take this, for the people who know this stuff, you take the simplicial chain complex, you take its dual, you get the simplicial cochain complex. That maps a k cochain to k plus one cochain. That's d. That's a discrete d. So they discretize d. And then they discretize d star because they could use the L2 inner product of two cochains by converting the cochain by this one-to-one correspondence into a Whitney form and just integrating the two of them. So they get a combinatorial d star. And then they try to show the eigenvalues of combinatorial d star plus d star d converts to the eigenvalues of the true d star plus d star d. And they have a hell of a time. They actually succeed, but it's really a mess. And they say, we think this is a mess because we think our d star, our discrete d star, is not consistent. They didn't use the word consistent, but what they had is exactly the notion of consistency. It can be described as consistency of this d star h, their combinatorial coderivative, in terms of Whitney forms. And I won't go exactly how into it, but here you see you take so basically you take a smooth differential k form, you evaluate its integral on the k-dimensional faces, that gives you a k cochain. You apply this combinatorial d star to it, you get a k plus one cochain, and you compare that to the true d star of u. And you'd like to show that those converge to each other, and they couldn't show it, and they said, we conjecture it's not true. And they even gave a counterexample to it, but the counterexample was wrong. Because the counterexample was on a uniform mesh in two dimensions for one forms, and Smits proved that it is consistent on a uniform mesh on one forms in two dimensions. And he pointed out where the error in the counterexample was. But he left open lots of questions. Is it consistent on a uniform mesh in n dimensions for one forms? Is it consistent on a non-uniform mesh, some other mesh than a uniform mesh for one forms in two dimensions or in n dimensions? And how about for k forms, not just one forms, is it consistent? And that's the question we were able to answer with these collaborators, published in Transactions in 2014. And the answer to the questions are, 1 is yes, 2 and 3 are no. So uniform mesh is not that easy to define in higher dimensions. Here's pictures of uniform meshes. In 2 dimensions, you just take each triangle and divide it into 4 equal triangles, similar congruent triangles, and keep doing that. In 3 dimensions, a little more complicated to define. But we were able to prove the same theorem as Smits did in 2D in ND with this definition of uniform. It is consistent. The one form Hodge d star is consistent. Then we looked on a non-uniform mesh, and we took a very uniform non-uniform mesh. You might call that uniform, but it doesn't fit the definition of uniform. And on this mesh, this crisscross mesh, which we saw before in one of my counterexamples, and on this mesh, the method is not consistent. And we did that by doing it analytically. We took a super simple form and actually were able to compute by hand its d star h And here d star u, the exact d star u is just a linear function, but d star pi hu, the discrete one, is some crazy oscillatory thing that doesn't converge. The yellow doesn't converge to the green. And finally, we gave a numerical proof that if you go to two forms, even on a uniform mesh in 3D, it's not consistent. We just computed the consistency error and refined our mesh up to 200,000 elements, and it's not going to zero pretty clearly. So that closes the conjecture of Dojuk and Todi and closes my lecture.
Well, thanks, Doug. We are sort of late, but maybe time for a short question from the audience. No questions? Oh, yeah, go ahead.
So it seems that the method is very sensible to the way you choose the mesh. So isn't this
the unstable methods are very sensible to the way. So what you're dying for is a method that'll work on just about any mesh and it'll be nice. That you'll get if it satisfies the Fick hypothesis of subcomplexes with bounded cochain projections. Then you don't have any of these weird pathologies that we were seeing. But once you get away from that, you get away from a clean structure-preserving method, all sorts of funny, bad stuff can happen. That's
scary, actually.
Scary, yes.
Yeah. Yeah, thank you.
Further questions or comments? No? Well, if not, let's thank Doug Arnold again.
Okay.